Hello everyone, and welcome to the first British Society for Geomorphology seminar of 2026. Just to let everyone know that this seminar is being recorded, and so it will be put on the BSG YouTube channel, which will be linked from the website at a later date. Please feel free to share it with anyone who might be interested. The BSG have lots of exciting seminars planned for 2026, so do consider joining if you'd like to receive communications about these, because yeah, you'll get notifications through the newsletter and various other emails, and you'll also have access to other benefits such as free online access to Earth surface processes and landforms, and access to research funding, things like that. Today, I'm really pleased to welcome Gerd Masselink, who is a professor in coastal geomorphology at the University of Plymouth, where he leads the Coastal Processes Research Group and is founding director of the Coastal and Marine Applied Research Consultancy. Gerd will be talking about the morphodynamics of the Slapton Sands barrier within the wider context of Start Bay in South Devon. No doubt you'll have seen all the news coverage of the recent storm damage to the road located on the barrier crest. Therefore, Gerd's reflections on barrier system dynamics gained from over 20 years of research at Slapton will be of interest to all of us. Please could I ask if everyone could stay on mute till the seminar ends, and then there'll be a chance to ask questions once Gerd's finished presenting. But for now, Gerd, over to you.
Thank you, Nish, and also thanks, Paul, for inviting me for this seminar. It's a very exciting time for me this month and the previous one because of the storms. We've been doing a lot of what we call storm chasing on various beaches in the southwest of England, and especially we've also been looking at the Slapton Sands barrier system, which has incurred a lot of damage during the storms we had recently. I just have to say I'm very excited about this, but I think it's always quite easy to forget there's a really important human dimension to this as well. Their livelihoods are directly being affected by the types of things we're really excited about. So I think we just have to bear that in mind, that these are serious issues for local communities, and in this case the village of Torcross and the people in the surroundings. We've been doing a lot of work on the Slapton Sands barrier system and Start Bay in general over the last 20 years. I have to acknowledge the funders, mainly NERC and EPSRC, for funding a lot of the research. But I guess especially I need to acknowledge the contribution of my research group, the Coastal Processes Research Group, who have been doing most of the work in this area in the last 20 years. A bunch of researchers and students have all been involved with the work that I'm reporting on. I'll give you a brief introduction to the study area. I think it's important to know where we are, what's happening, and how the area has evolved. I'm going to give a historical overview of the things that have happened in this area and that have led to well, the almost destruction of the village and the road in the previous months. I'm going to then talk about some of the in-depth research results that we've obtained in the last 20 years at this location. And then I'm going to try and sort of put it all together, try and explain the historical overview of what's been happening in terms of the research results, and give some sort of overview of why things have been happening at the rate that they have been happening. And then there'll be some take-home messages. The future, I think, is very much up for discussion. I think everyone's got views on what should happen. I've got very strong sort of views in terms of the physical science, but like I said, there's also a very important social, economic, political dimension as well, and maybe we can explore a little bit that at the end of this presentation. So I guess just describing the area, Start Bay on the south coast of Devon. It consists of 4 beaches that sit in the bay: Slapton Sands, B Sands, Hall Sands, and Blackpool Sands and B Sands. There are a couple of villages which I'm going to be referring to. There is Torcross, is the current village. I'll briefly refer to the lost village of Street Undercliff, and I'll also be referring to the lost village of Hall Sands that sort of fit within the historical overview. There is a so-called banner bank called Skerries that extends across most of Start Bay. This bank is very shallow, a couple of meters water depth at low tide, which means it's got some implications for wave transformation. It's also a very large bank. It extends across half the bay. Most importantly, and I'm going to refer a lot to this, is that this area is characterized by what I call a bidirectional wave climate. It has either waves from the south that come from the Atlantic, which are the blue arrows. Everything in blue in most of my diagrams refer to the results of southerly waves, or we have the easterly waves being generated across the channel. And this bidirectional wave climate generates a bidirectional longshore sediment transport system that's absolutely key to explaining a lot of the things that are happening, a lot of the dynamics on this particular site. It has a macrotidal tide range. The spring tide range is just larger than 4 meters. The flood currents sort of sweep into the bay on the outside of Skerries, and the ebb currents sort of sweep out along the inside. And it's actually thought that these tidal currents are responsible for forming the Skerries Bank as a sort of a giant eddy. History is important here. History is important in anything to do with coast, I think. Sort of the Markovian inheritance is relevant. What we have now is largely a function of what happened in the past. So 18,000 years ago, obviously, the depth of the Ice Age, people would be walking from France to England on foot. We pick up the story at about 8,000 years ago. Sea level was about 18 to 20 meters lower. The whole area of Start Bay would have still been dry. Sea level was rising, and as sea level was rising, it brought I call them proto-barrier islands up from lower down the shelf, consisting of mainly flint material and chalk, derived from the chalk rocks that are about 40 kilometers offshore. We know that there was this barrier chain because there's evidence of saltwater and brackish deposits in the bay obtained by coring, which suggests that there was an intertidal barrier lagoon complex protected by a barrier chain with gaps in it with tidal inlets. Then slowly, as sea level was rising more, those barriers got pushed more and more into the mainland, filling in the embayments of Hull Sands, B Sands, Slapton Sands, and Blackpool Sands. Up to 3,000 years ago, there was still a gap in between the barrier of Slapton Sands, and there was I guess, an intertidal environment, an estuarine environment behind it. Then around 3,000 years ago, the barrier closed and the Slapton Lay became a freshwater lake. The Skerries is formed after the barriers had passed, so the islands of the Skerries is relatively recent, and now there's maybe the fear that the barrier will be breached again, potentially Slapton Sands becoming fresh salt water again. There are a bunch of shoreline management plans. One is related to Tor Cross, and I think it's important to bear in mind that the Tor Cross section has a hold the line policy until 2055 and a managed realignment strategy until 2105. So first hold the line and then moving into a managed realignment policy. Most of the road that runs across the barrier, it's called the Slapton Line, has a managed realignment policy advice now and certainly also into the future. The Slapton Line Partnership is a group of stakeholders that formed after the barrier got breached or the road got damaged in 2001. It's a group of stakeholders, local people, but also Environment Agency, Natural England, and a whole bunch of other people that are basically seriously looking at the prospect of potentially losing the road and looking for alternative ways once the road has to be abandoned. Very interestingly, most recent correspondence or documents from them is a Slapton Line adaptation plan, which acknowledges that there will be a point in time where the road has to be abandoned. And they specifically say until a point happens where triggers are met that require the road to be abandoned. But as you can see, it says to be agreed. So it's certainly not written in stone. One thing we might want to look at is whether the triggers have been reached now. In terms of the history, the continued history, we have a bunch of lost villages. People probably don't really know about Street Undercliff, which was a village at the northern end of Slapton Sands, was established several hundred years ago, but was actually abandoned after a major storm in 1782. Interestingly, then, on the opposite end of the bay, a new village was established, Hull Sands, 2 years after Street Undercliff was abandoned. So I suggest maybe the people from Street Undercliff moved to the other side. Dredging started 120 years ago, over a 4-year period, to get gravel for the Plymouth dockyards. The beaches was disappearing, the dredging stopped. Hull Sands was actually completely demolished in 1917 during a major storm because the protected beach was gone. But I just have to point out as well that the beach levels in front of Hull Sands kept lowering well after the village was abandoned, and also well after the dredging stopped. So maybe there's something else going on. The village itself, or the beach itself, of Tor Cross, pretty healthy, wide beach in the early 1900s, certainly up till 1960 probably, a very wide beach, and notice all Tor Cross. But it is clear that the village is clearly built right on top of the barrier. It's not built behind the barrier, it's actually on top of the barrier. Then there were some major storms in 1978. One major storm had almost destroyed the village of Tor Cross. Lots and lots of damage was done. Similarly, a lot of damage was done in B Sands, and it was concluded that a seawall had to be built to protect the village of Tor Cross as well as B Sands from further damage. The seawall was finished in 1980. Relative stable conditions after that, but then in 2001, another storm happened and damaged a very large section of road. This was when people started to realize that maybe the road had to be abandoned at some point in the future. Initially, there was a lot of resistance to the idea, but with sort of after consultation and sort of discussions that were part of the Slapton Line partnership, local residents probably accepted the fact that it was a matter of not a matter of if the road was going to be abandoned, but when, and certainly not in 2001, because in 2001 repairs were done to the road. A short section, 250-meter section, was managed realigned, brought further to the back. Fortunately, there was space to move towards the back because the barrier was quite wide where it got breached. But yeah, this event prompted the founding of the Slapton Line Partnership and started the whole consultation process. Relatively stable condition again over a 20-year period from 1990 to 2010. Here we see the beach again being incredibly wide, but protected by a seawall. When I started working on Slapton Sands in 2004, 2005, one could literally step off the seawall onto the beach. And it's very different now, as we will see in a minute. Then a major set of the winter 2013-2014 winter was one of the, well, probably was the most energetic winter on record since the 1950s. Did a lot of damage in the whole of the southwest coast, and some of you might remember the Dawlish Railway being damaged and closed for several months. Basically, the beach levels in front of Tor Cross were lowered so much that the seawall started sort of leaning forward. A big crack appeared where the seawall joins the road, suggesting that there was this leaning forward happening. You can see the crack here on the left side of the image. The Environment Agency decided that it was not safe anymore, and it was decided to strengthen the seawall, basically by pushing in, or pulling in, pushing in, I guess, 8-9 meter long sheet piling a meter in front of the base of the seawall, and then filling that gap up with concrete. The cost of that whole process was £3 million, and it was emergency funding which sort of was used for this. Also, some repairs were done to the road at the sort of the northern end of the seawall where the cursor is, where also some sheet piling was installed because the road also got damaged. This sort of happened following the 2014 winter and the 2016 winter. Also, damage was done to the village itself, but it was mainly focused on the road and mainly the seawall, really. Impacts on the rest of the road were also quite dramatic. It's clear that the barrier wants to move landward. Overwash happens a lot, and lots of shingle gets chucked onto the road, and the policy is then to push it all back onto the beach, even though the barrier wants to move really. Then we had another major storm in 2018, more damage to the road, lots of damage to the village as well. But you can sort of see, interestingly, that there's also a lot of, again, the tendency of the gravel to be chucked over the seawall. And this particular storm was an easterly storm, and actually brought, and we'll talk more about it later, brought a lot of gravel and shingle back in front of the Torcross seawall, and that almost like provided a ramp to go for the waves to go over. But again, lots of damage to the road, a different section to the 2001 storm. Again, more repairs required, and that would have been the third time that this has happened since 2001. And then I'm going to show you this clip from what happened last month. This is Storm Goretti. No, this is Storm Chandra. No, this is Storm Ingrid, number 3. This was that's the most damaging one. And this is the event that not caused it, because it was a series of events, but this was the most significant event that did most damage to the village. So let's have a look at a bit of the damage that was done. A lot of damage to the houses, roof tiles missing, all wall sections pushed in, a lot of glass damage and windows as well. The crack started to reappear, although the Environment Agency thinks it's not an issue, not as big as an issue as it was previously. And these sheet piles were initially in front of the repaired section of road. These are shorter sections of sheet piling than the sections in front of the seawall. And this is the aftermath of this series of storms in January, and then a few more storms in February. And I'll talk more about the individual storms in a minute. But this is the situation at the second week of February. And you can sort of see a major section of road at the end of the seawall taken out. Then there's a short section with the road still intact, and then another larger section where the half of the road was taken out. It's also recent estimates of the cost estimated to repair this, and it's estimated at £18 million to repair the road. I'm not quite sure whether that means, I guess that means repairing the whole road section and shoring it up, I presume. Just for reference, the repairs to the seawall in 2016 were £3 million. And again, for reference, I seem to remember that the Environment Agency or the government has announced £30 million for coastal adaptation, £30 million for the whole of the country. So you can sort of get a feel for how much, how likely it is that they're going to spend half of that on the road. Okay, so let's look at these events and sort of put them into a bit of context. This is a time series of wave information taken from the Southwest Coastal Monitoring Program. This is data that's freely available, and we use a lot of this data to study beach change and waves on the Southwest Coast. So it's basically significant wave out on the x-axis, and starts on the 7th of January and finishes on the 7th of February. These are the first two events, and the red line here indicates actually it's an official storm threshold. It's the 1 in 3 month return period. So Goretti was the first one, a very short event that just about peaked the maximum. And then we had the series of really big events, Ingrid and Chandra, both registered storm events, and a few more events as well that were very energetic. And then what these storms did, the Goretti lowered the beach levels in front of the seawall. Ingrid and Chandra and that whole period did a lot of damage to the village and further lowered the beach levels. And then to top it all off, there were two, one big and one slightly smaller easterly wave event, which are unnamed storms because they didn't exceed the storm threshold, but they did the damage to the road. So the damage to the village was done, and the lowering of the beach was done by these first set of storms, which were southerly storms, and the damage to the road was done by the unnamed storm in February, which was an easterly storm. Just to put them into context in terms of wave power, it's clear that these the ones that did the damage to the road, the easterly storms, are actually a lot lower wave power than the storms that happened in the second half of January. Ingrid and Chandra were much more energetic, and were hence officially storms, whereas the easterly events were not official storms. the footprint of these early storms, which is just quite a nice addition to the material that's on the Channel Coast Observatory. It just shows how widespread these events were. And whenever you see a red dot, it basically means that that particular event exceeded the storm threshold for that location. We can see that both Goretti, Ingrid, and Chandra, all of them actually were very widespread events. But the size of the bubble indicates the severity of the storm in terms of their return period. The blue arrow points to the Start Bay Slapton wave buoy. What it does mean is that there were storms, but they were not exceptionally rare storms. They were more frequent than a 1 year return period. So there were storms, but not particularly severe. And again, the easterly storms did not register. Some idea of what the beach conditions were like using the CoastSnap data. Well, you can sort of see pictures taken by the CoastSnap facility that also the Southwest Coastal Monitoring Program arranged. This is basically citizen science. People can take pictures from a fixed position, and then we can actually get a lot of useful information from it. What it basically shows is very low beach levels at certain times, certainly in the start of 26. The photo of me is a picture after all the events and shows a 1.5 meter drop in beach levels relative to the base of the seawall, but actually a couple of days earlier it was more than 2 meters. So remember, I used to be able to step off the seawall in 2004, and in this particular picture we're probably looking at beach levels that are 6 meters lower than they were 20 years ago. Okay, so that sort of gives you a bit of an overview. I'm going to now show some advanced sort of research results that we've obtained in the past few years, and then sort of try and sort of explain some of the processes in more detail. These are all done by a large number of staff and a series of PhD students. Both survey work and process measurements of waves and currents were done. Now, this is the first one. Amaya Ruiz de Alegria Azabaru. He wasn't the first PhD student, but was the first PhD student who looked at beach morphology on Slapton. She basically surveyed the beach at a large number of locations every month on her own, in addition to doing post-storm surveys. I have to say she worked really, really hard, but she did park on the A379, the main road, whenever she had to go from one survey point to the other, which is something we wouldn't do now. She collected an awful lot of data, and she was specifically looking at the effect of storms here. So what this plot shows is basically the along coast change from Torcross to the northern street end. And on the y-axis, it's actually the changes in beach volume for different profile lines. So every bar represents a different profile line. And this represents the southerlies. That's the easterlies. This is all the storms. This is the calm weather conditions. And this is the net change over the whole 2-year period. And then she's broken down the beach into the supertidal area, which is the bit above mean high water spring, the intertidal area, and then the total volume, so the intertidal as well as the supertidal area. And sort of these are the two different wave conditions that are really governing the changes on Slapton Sands. And really the message is quite simple and logical, is that with southerlies, the southern section of the beach loses a lot of sediment, whereas the northern section gains a lot of sediment. Whereas with easterlies, the southern part gains sediment and the northern part loses sediment. So we can sort of see that these different wave directions generate different sediment transport directions. In addition, we also have to point out that easterlies tend to strip sediment from the top of the beach, whereas the southerlies tend not to do much change to the top of the beach. So easterlies move things southward and take sand or gravel from the top to the bottom, whereas southerlies tend to move shingle from the southern end to the northern end. And then the total changes over this whole period actually shows a removal of sediment from most of this sort of area, and then deposition of sediment to this area. And we can see also that we're not conserving mass, and explanation for that will come in the next slide. So Mark Wiggins was the second student who looked at beach changes here. We introduced the concept of a total embayment survey. So we would use LiDAR data, drone data, walking survey data, as well as bathymetric surveys using multi-beam and single beam to basically count every single pebble in the whole start bay embayment. And then we were doing a full survey two periods apart, and then we could look at the changes that happened between the two periods. What this slide on the left panel shows basically the changes that have happened from 2013 to 2016 during this really energetic period with this really strong southerly storm action. And what we can basically see, if we focus on Slapton Sands, the whole southern section is red, which means we've lost a lot of sediment. The blue section is gaining sediment. So we can basically conclude from this that the sediment was removed from this section and was transported to that section. That allows us to calculate the sediment flux as well. So we worked out that about half a million cubic meters of shingle was moved from the south to the north over this period. This plot here basically shows all the data together and compares the positive values and the negative values. And what it basically is used to demonstrate is that we get a perfect balance between blue and red, which means that we have a very nice closed sediment cell. Sediment is not leaving start bay and sediment is not coming into start bay. So when you lose something from one end, you have to gain it from another end. We also have another period, which is the southerlies. And here we go, mainly see red colors in the northern section and blue colors in the southern section. This particular period was relatively weak easterly wave events dominating the wave climate, and it actually moved 150,000 cubic meters shingle back to the south again. Now we're about to do another full embayment survey in the next month, and then we can start comparing 2017 with 2026. You sort of imagine that this is incredibly time consuming to do this whole full survey, but this gives us some really nice insights into how the shingle moves up and down the beach. As part of the Blue Coast project, we had a number of PhD students, but particularly we had a postdoc called Jack McCarroll, who we basically were targeting a storm event in Start Bay. And we were lucky in one way to catch the storm Emma, which was the biggest easterly storm event on record. We were also unlucky because it did a lot of damage to our equipment. We lost a lot of equipment because this was a storm that was a bit too big to handle. Just to give you an idea how big the event was, it was traveling on the back of the beach from the east, which was a really cold period. And Storm Emma had peak wave heights of more than 5.5 meters, which is practically unprecedented for this stretch of coast. And this plot shows the waves are predominantly from the east. So it was an easterly storm wave event. We had lots of wave sensors out, and they all show very similar wave heights. All these lines in this plot on the left are profiles that we regularly surveyed before the storm, during the storm, and after the storm. It was a real big team effort, and it certainly was the coldest I've ever been on the beach anywhere in the world, was during this beach from the east period when we were all setting equipment out. But we got a really interesting data set out of this. What this really shows is from all these profile data, the bottom plot basically shows the changes in beach volume during this particular event. So anything that's positive is accretion, anything that's negative is erosion. So if we focus on Slapton Sands, we can see we lost a lot of gravel from this sort of northern end of Slapton, and we gained quite a lot of sediment from the southern part of Slapton, which is sort of this section here. So again, confirming this southward transport of shingle. Because we had such high resolution data, we could actually derive long-term sediment transport rates from this, and that's what this plot shows. So it's actually using the beach volume measurements to get an insight into transport rates. And just to, again, put a sense of scale on it, these numbers are very large. We're looking at 200,000 cubic meters of shingle being moved by a single wave event. So this is why the beach levels change so much on Slapton Sands and transport predominantly or almost exclusively towards the south. Then we also have a long-term time series. We survey the beach every month since 2007, actually. I'm not sure why this is 2011 start, but it doesn't really matter. Since 2007. And we basically looking here at the beach changes by this profile 1 at Tor Cross, which is the blue line. And the northern end is the red line, profile 18. And we can see these lines diverging. It's basically what it's telling us, that over this period, the southern section has progressively lost shingle, whereas the northern section has progressively gained shingle. There's some ups and downs, and these ups and downs are very strongly related to the different times of storm conditions. So this is the beach from the east storm event. It lowered the beach levels in the northern end, and it increased the beach levels at the southern end. And if we look at this 2013-14 period with big southerly storm events, what we can see here is that we gained sediment at the northern end and we lost sediment at the southern end. So the beach levels change very much in response to the wave directions, which in turn drive longshore transport. That's sort of conceptually what's been going on. I guess I have to acknowledge Tom Hamilton, who's our current PhD student who went out last week and just prepared this plot for me. So it's his role now to do these surveys and generate these summary plots until a next PhD student comes along. Okay, I'm going to take a little detour and then bring you back and trying to put all the different sort of elements together. And I have to sort of take a bit of a step back and look at and try and explain what controls our climate and weather in the southwest. What are the big weather systems that control this? I'm sure you've all heard of the North Atlantic Oscillation, or the North NAO. And it's basically a hemispheric weather situation that's characterized by a low pressure system in the south and a low pressure system, so in Spain, North Africa, and a low pressure system north of us near Iceland. That is the predominant sort of weather situation that we have in winter, talking about winter conditions here. This pressure difference generates westerly airflow from the Atlantic, and this is what brings us, most of the time, brings us the weather, brings us the wind, brings us the rainfall, brings us the waves, brings us flooding events, brings us all the bad stuff, but also at the same time makes the winters relatively mild, but wet at the same time. So if this pressure difference between the north and the south is relatively large, we talk about a positive NEO, which means that the pressure gradient is stronger than normal. We get stronger westerlies than normal. We get very weak easterlies. We get mild and wet weather. We have a lot of flooding, river and coastal flooding. We basically see enhanced Atlantic storminess. Sometimes this pressure difference is less than average, and we talk about a negative NEO. We still have a high pressure system in the south and a low pressure system in the north, but it's not as, the gradient is not as strong. Our westerly airflow will weaken. We tend to bring in more easterlies, which bring cold and dry weather, and we get less flooding, less big waves. We have reduced Atlantic storminess. So it's a really important concept to understand that the weather we're getting is obviously depending on this pressure gradient that is across the Atlantic. And we can demonstrate how this NEO relates to our wave conditions, because if we look at the correlation between the NEO value and the wave conditions all along the Atlantic, wherever we see red, we basically see that we have the wave conditions during the winter are positively correlated to the NEO. So the stronger the NEO, or the more positive the NEO, the larger the waves in the red area. The weaker the NEO, the smaller the waves that we're getting. We see this statistically split in correlation, but we've subsequently discovered by working with French colleagues that we can come up with another climate index, which we call WEPA, the West European Pressure Anomaly, which is now between the Azores and Ireland. It's a similar idea than NEO, but it's a smaller area. And that actually explains much better a stronger correlation between the value of this WEPA parameter and the wave conditions in winter for our part of the coast. So what we're seeing here is that WEPA very strongly positively correlated to the waves from the Atlantic. Now, these NEO and WEPA are they go up and down like a yo-yo. They're largely uncorrelated, as you can see in this scatter diagram. There's no correlation between the two, which means that they both explain something different in our waves. We can also see there's a strong trend in NEO towards more positive, whereas WEPA seems to be going up and down a bit more. So this is the key slide here. It's a lot of information in it, and this is sort of trying to bring it all together. It's trying to bring in NEO and WEPA, the wave climate, the easterlies and the southerlies, the northward and the southward sediment transport, and the beach level changes, all trying to bring it all together and then trying to explain how we got where we are, but also explain some of the things that happened in the past. And it's a bit of a detective story because we have limited information on waves and beach levels, and we want to go further back. So we're looking for proxies for these different processes. So it's a bit of a journey that I'm going to take you on. So this top panel shows the wave power in Start Bay, where blue indicates wave power towards the north and red indicates wave power to the south. We can sort of see this is the 2013-14 winter. This is the 2016 winter with lots of southerlies. 2018, that's the beach from the east. So we can sort of see our familiar phenomenon that I talked about earlier. The second panel shows the measured changes in the beach level, and we can see again, seen this before, these responses in the northern end and the southern end by these southerly and easterly waves. We talked about this before. Now, we want to do is try and relate the wave power to NEO and WEPA. So what these two plots show is for all the winters in this period, every winter has a typical wave height, wave power from either the east or the southerly wave power or easterly wave power, and I've correlated it to the value of NEO. So whenever we see, so this plot shows the relationship between southerly and easterly wave power and NEO, and what we can sort of see is that the easterly wave power in red is very strongly correlated to NEO. The more negative the winter NEO is, the stronger the easterly wave power is. There's less of a correlation with the southerly wave power, the waves from the Atlantic. On the other hand, WEPA shows no correlation with easterly wave power, but shows a very strong correlation with the Atlantic wave power. So by having both NEO and WEPA, it tells us something about what we can expect in terms of waves from the Atlantic and in terms of waves from the east across the channel. So what we've done, we've designed this parameter called the Wave Directionality Index, WDI, which is basically a measure of the balance between the southerlies and the easterlies. So we say it's a positive value if the southerly waves are more dominant, a negative value when the easterly waves are more dominant. I'll show you some examples of that in a minute. We also introduced another parameter, which is the beach response, which we call the rotation index. And that rotation index indicates how the profiles at opposite ends of Slapton Sands respond. So if profile 18 gets wider, profile 1 gets narrower, we're talking about clockwise rotation, is a positive value. If the northern end gets narrower and the southern end gets wider, we talk about an anti-clockwise rotation. We talk about a negative rotation index. So now we see how that works. So first of all, here we have the WDI, the Wave Directionality Index, which is a combination, it's the balance between the southerlies and the easterlies, and the beach width at the southern end. And we can see that as this parameter becomes negative, the beach at the southern end gets wider, which is basically anti-clockwise rotation. If WDI is very positive, our beach at the northern end becomes wider because we have the southerly waves moving sediment to the north, making the beach in the north wider, meaning a clockwise rotation. And then the final sort of plot is then linking WDI, so this proxy for balancing these two wave directions, together with the rotation index, which is like I guess it's a proxy, a single parameter that indicates wave response or beach response. And we can see a correlation between the directionality index and the rotation index. So this is sort of the concept here. If we can parameterize WDI, the wave directionality index, we can predict beach response. This is all the data we have. We don't have a longer time series. So now we need to look for proxies. So we have wind data, and that just sheds a little bit of light on what's going on. We do have wind data from 1960. We don't have wave data from 1960, but we do have wind data. And this is just a plot showing the winds at Plymouth, comparing the conditions under which the winds are strong enough to generate waves that are larger than 2.5 meters. So storm waves from the east, the number of hours that we can expect storm waves from the east over this period. And we can see there's a drop in the length of the number of hours that we get stormy easterly conditions according to this wind record. The middle plot shows the southerly waves, the sort of remain more or less constant, maybe a small increase since the 1980s. And if we look at the percentage of waves from the east over this period, we can see a distinct drop in the wind from the east. So someone seems to have switched off the easterlies, and we obviously need to update this because this only goes to 2016. But there's already something in the wind data that suggests something that's going on. Okay, so what have we done here for proxies? So since we have wind data from the 1960s, we also have modeled wind and wave data. So we can now maybe look at the wave directionality index, not based on measured wave data, but based on modeled wave data. And that's what's sort of shown in these bars. These bars basically indicate, using modeled wave data, how this wave directionality index has changed since the 1980s. Unfortunately, we don't have a longer model wave record, so at least we can extend the measured time series from 2010 now to 1980. And then we can basically compare, we basically did a multivariate analysis comparing the modeled wave directionality index as a function of NEO and WEPA, because we know they're correlated. NEO encourages the southerlies, or encourages the easterlies, sorry. WEPA, positive WEPA, is the southerly. So combining these two parameters, we get a reasonably good predictor of WDI, which is the black line that follows the modeled wave data quite well. Now, because we have NEO and WEPA data much further back to 1900, we can now generate a time series of the wave directionality index based on NEO and WEPA. And we know from the previous slide that that might give us some insight into how the beach responds as well. So what we've done here, we've used the modeled predicted wave directionality index, the black line in the top panel, and we generated a cumulative time series of that. Now, the idea being is this: if you have many, many years of a positive wave directionality index, it suggests that you have a predominance of southerly waves rather than easterly waves. That would generate northward transport, not southward transport, and that would generate a beach rotation that is positive, not negative. So this cumulative WDI gives us some insight into how we would expect the beach to behave. So if we follow this curve, this red curve, and we start with I guess it's the end of the dredging, and we pick up the story at the end of the dredging of village of Whole Sands, we have these phases where we see the WDI cumulative index going up, which basically means these are phases where the southerlies are more prevalent than the easterlies. And when these curves go down, we see a prevalence of easterlies relative to southerlies. So we basically have a time series, a surrogate time series of northward transport and southward transport, parameterized by WDI. Now, can we link that to our beach response? Well, this is the end of Whole Sands, which is in the middle of this northward transport. So we suggest that by the time that the cross happened, most of the beach sand was removed from Whole Sands and moved to the north. We have another big dip, which is the storm damage that happened in Torcross and B Sands, again after maybe 10 years of beach lowering. Then we have the 2013-14 and the 2016 storm damage, again after significant lowering, after a period of prevailing southerlies. And here we have the periods of easterlies. And remember, the easterlies move shingle back from the northern end of Slapton Sand to Torcross. These are the phases with the relatively stable beach. So this is how we can start putting these sort of things together. So the storm damage that we had last month happened at the back of a period of lots of southerlies that moved beach to the north, lowered the beach levels, and then the beach was so low that the easterly then did a lot of additional damage. So hopefully the picture is reasonably clear. So Slapton Sands is highly dynamic, impacted by extreme storms, longshore transport, also about sea level rise, but we haven't really talked about that, but that's sort of an underlying thing. The critical infrastructure and housing, the village of Torcross and the road, is placed in a dynamic zone of waves where the beach is expected to naturally change. So it's not a miracle that we have problems. The bidirectional wave climate is key to understanding these dynamics, and is controlled by large-scale weather patterns, and they can be characterized by NEO and WEPA. Prolonged southerly waves leave Torcross hugely vulnerable to extreme easterly storm events by lowering the beach level. There's been an increase in southerlies relative to easterlies since 1980, which has resulted in a sort of a large-scale rotation of Start Bay. And sea level rise will only increase the vulnerability and dynamics as it enhances extreme storm impacts. Sea level rise itself will not do anything, but it allows these storm waves to act higher elevations on the beach profile and therefore have a major impact. And the storm damage of 2001, 2013-14, 2018, 2026 pulls into question even the short-term future of Torcross and the Slapton line, let alone the medium to long-term future. So in terms of discussion, I don't really want to, start improvising what I think should happen, but I think these are all really relevant questions that I think my presentation might provide some insight into. So will the road be repaired? Should it be repaired? Who should pay for it? Is there an alternative? And again, who should pay for that? Should or will the seawall be repaired? How long will it be maintained? Who should pay for that? Should Torcross be abandoned now or when in the future? And again, who should pay? Who should facilitate that from happening? I've been looking a lot at the social media following the damage, and there's a really strong sentiment in the community that's expressed by Patrick Meany from Torcross. They basically seem to have forgotten all the discussions that were done as part of the Slapton Line Partnership. The idea that it was a matter of when and not if has been completely thrown overboard, and most of the local people want to have the road repaired. They don't want plan B. They want the road repaired because it's essential. A few voices, what I call the voices of reason, which is, okay, bearing in mind that this has happened before many times, so the reasons why it happened, maybe we should stop protecting, and we should maybe start thinking about retreating, abandoning the road, and not repairing it, and not throw more money at it. I have views on this, but maybe this is not the forum to talk about that. But I'd like to hear any questions or comments on this. So thank you very much.
That's great. Thanks, Gert. That was an excellent insight into the driving forces at Slapton and within its wider context as well. That was great. Well, I'm sure there are lots of questions. Therefore, yeah, if people want to either put their hands up or put them in the chat, I'll try to get to them. We've got about 10 minutes left. So it looks like Ian Reid, I think you're first in the list.
Always.
There we go. Excellent. Go ahead.
Right, Gerhard, a very interesting talk and very well presented. Thank you for that. I would dwell on the physics, but in fact, I want to actually just pursue that last item if I can. The controversy, in fact, and the political sensitivity of this thing, in fact, is indeed nationwide.
Yes.
And in fact, it cannot be, in fact, actually left to the southwest, in fact, of England to actually decide how this goes. So yeah, my neck of the woods at the moment is East Riding of Yorkshire. The Holderness coast is going back at the fastest rate in Europe. Yeah. And the county council is currently, in fact, paying people to set back. In other words, in fact, they're actually establishing the houses away from or homes away from the actual coastline itself. Yeah. So to all intents and purposes, in fact, were we to spend whatever it was you said, in fact, half of the budget, in fact, on Slapton, it strikes me, in fact, there's going to be a lot of people in the rest of the country going very unhappy about the fact that it's all being spent in the southwest of England.
Yes, absolutely.
Over and out to you.
No, I always refer to Slapton as a bit of a microcosm or like an example of things to come. And you might say the same of the Holderness coast, because these are not isolated instances. This is going to be a nationwide problem. And we can talk about it for half an hour. But clearly, there's not enough budget to deal with all of this. I also feel there's a danger of doing what they're doing at East Riding, with setting a precedent, because I know they're buying people's houses and then they can go. The same happened at Haysborough, where people got paid a decent price of their house and then they left. That is totally unsustainable. And I do think we need nationwide, we need some sort of approach to deal with this, because this is just only just started. This is only going to get worse and worse in the future. And if we don't come up with something that's a consistent approach to this, I don't know, I just feel slightly uncomfortable with the whole idea that as soon as you have a village that's having this problem, a local MP sort of steps in, argues for money to come from central government to sort it out, and then central government doesn't have the money. I can't quite see, a way forward with this, and I don't have a solution to this. But I fully acknowledge that this is a UK-wide problem that is only going to get worse and worse and worse. And buying people out is not a solution, because I don't think there's enough money for that. Nor is investing, doing protection for every single blip on the landscape that gets affected. That's not an option either. So people will have to get used to the idea that they will not be compensated, and yeah, I think that's undoubtedly going to happen. I think it's not an answer. It's just acknowledging that you're right.
Excellent. If we can move on to Uwe, you got hand up.
Yes, interesting talk. Well, apart from the timing of when one should abandon this, that is probably the 70s when the first damage happened, or in many other places it's the 50s and 60s where one shouldn't have repaired stuff. But the question from the science point of view is, what is water level to do with all that? Because obviously your graph of the wave gauge over the last few months shows that these storms happen at different water levels.
Yeah.
And when you go back in time, you don't have water level. So how can you and you don't have wave period or something. So how can you, which probably in the southeast has an impact as well. So how can one extrapolate all this Weber stuff into actual beach change when there's more than just sort of the pressure?
I guess the fact that the water level sort of averages out in, and what I'm trying to explain is here. I mean, I thought you meant rising sea level, but you actually mean the concurrence of a storm event with a spring high tide rather than a neap high tide, and that's going to have a major impact. Yeah, I think if you're looking at the long term, the probability of a storm happening at a certain tidal water level is, these are independent, right? It's not like the storms are more likely to happen at a spring high tide than a neap high tide. So that they are unrelated, they're uncorrelated. So if you're looking at a period of, let's say, 10 years, and you look at a typical Weber value, and you say, okay, this is a very stormy period, we can expect at least 25 storms from the Atlantic, then they're going to be randomly distributed across the tidal frame. So I think the effect of the tide is going to average out. That is different from being able to predict the effect of a single storm, because the effect of a single storm will depend on whether it's a spring tide, whether it's a high tide or a low tide. But I think on the long run, it's going to average out, which is why this cumulative Weber or the cumulative WDI, it's one that sort of integrates over long periods of time. It doesn't really look at what happens in a single year, it just integrates it over time. So if that WDI keeps sort of climbing up, that just indicates a period of sustained Atlantic wave action, number of storms in the Atlantic, some of which will coincide with the spring high tide. I think that's how it works. It's a long-term averaging out of the impact of the tidal levels.
Okay, thank you.
Right, and then, sorry, I'm going to say this wrong, but Suhail?
Yes, thank you. Thank you for the talk. So knowing that Slapton Sands is high dynamic, if it were left, let's say, undisturbed and the village were abandoned, do you think the lay behind it would eventually disappear permanently, or will it also remain dynamic, just shrinking, expanding, and reappearing?
It's a really good point. I forget what the guy, there's a local celebrity guy who tweeted something on this as well. I forget his name. I don't know. Anyway, I replied to his little film about expressing concern about Slapton Lay. And I said a couple of things here. One was that I think it's unlikely to breach in the next sort of 10, 20 years, because it is quite wide, the section of shingle. And shingle doesn't, has also the tendency to, or gravel has tendency to increase the crest as well as narrowing. So there's a natural protection that the shingle barrier can provide. By rolling back into the lay, it can prevent the breaching from happening. So that's the first thing. The second thing, if it does breach, it's likely to close very quickly because of these large long-term transport rates. It'll close very quickly because of that. Thirdly, the lay consists of two sections, an upper lay and a lower lay, and they can be very quickly and easily separated from one another. So you might lose, one of the lays might become salt water, but then the other one will still be fresh water. That's the third reason. Fourthly, there's examples of this have happened before at Porlock. Porlock used to be the Porlock barrier, or was a gravel barrier, and got breached in, I think, 1987 by a hurricane wave event. And the freshwater marsh behind Porlock got turned into a brackish water marsh. Natural England, English Nature at the time, they insisted on Porlock barrier breach being fixed because they wanted to retain the freshwater status of the marsh. In the end, it was decided not to do that because it was a natural process. And now the triple SSI freshwater marsh is now a triple SSI brackish water marsh. So there will be a change if it breaches, but it doesn't necessarily mean that the whole thing is destroyed. It's going to be replaced by something else. And there's some really interesting questions to be answered, whether one should stop a natural process from converting a type of coastal environment into another type of coastal environment. Although I can see the point that maybe it's not a fully natural process. The transition will be a fairly natural process. And from a scientific point of view, it would be extremely interesting to study. But yeah, I think that's a very interesting additional issue. That's not about socioeconomics. It's about how you try and keep the status quo of a coastal environment against the backdrop of climate change.
Thank you. Very interesting. Thank you for the elaboration.
Great. I'm just going to hop over to some questions that are in the chat. There's one question from Simon Hawkins, who asks about how far we're able to determine whether storm intensity and storm direction will alter under climate change.
Yeah. I mean, it's super good question, and I won't be able to say anything about this other than part of the motivation for us to go to WEPA and NEO was if we can actually get an understanding of how these big climate systems affect waves and actually thereby beach change, if the smart climatologists can predict the direction of travel for WEPA and NEO in the future, it gives us some insight into how the waves will change. I think there's some skill being developed in that area. I think we can already predict like 1 year in advance what sort of NEO we might get. So that might be okay for storm preparedness, but the real challenge is to get long-term predictions of NEO and WEPA, and then we can start looking at directional change in our waves. And I think the point to point out that on the south coast, bidirectional wave climate is ubiquitous, which means that what we've been showing for Slapton in terms of the rotation in response to changes in wave direction, that doesn't only happen at Slapton, that happens on all sort of beaches along the Channel coast. So any changes in dominance of southerlies versus easterlies will have an impact far beyond Slapton. So it is really relevant for us to obtain those sorts of predictions, but I don't know what they are.
Right, now if I could go to Ollie.
Yeah, thanks, Nish. Thank you. That was absolutely fascinating. Lots of questions, I think, but I'm particularly interested in practical terms in the significance of clustering of storm events.
Yeah,
I think your work has shown, certainly with incidents of damage to the road, for example, that role of the priming, event priming for subsequent damage. I wonder whether you've got a strong sense of the sort of relative significance of clustering versus any of the other conditions you're looking at, whether it's directionality.
We did some wavelet analysis on NEO and WEPA. And there seems to be like a 5, 6, 7 year sort of cycle in both of those. I mean, there's trends as well, but there seems to be like every 5, 6, 7, 8 years, there seems to be something going on with these cycles in WEPA and NEO, which means the clustering. I think you mean the clustering in a certain year, not within like five years you're done.
Yeah, without sort of
and then there's everything's coinciding again. Yeah. So even just looking at this looks a pretty random sort of thing, but it's interesting how there is a between 5 and 10 year sort of cyclicity. I wouldn't call it cyclicity, sort of a variability of that timescale in these climate indices, and therefore replicated in the waves, and therefore also replicated in the storminess. Yeah.
Great. I know we're overrunning slightly, but I'll just try and fit another. Is that okay?
That's fine with me, because no.
Excellent. A couple more questions. So, Ruth, I think you're next.
Hiya. Thanks so much. I'll just put my camera on. I honestly just intended to turn up and listen, but honestly, it's been such a great talk, as it's already been said, and this is very close to home. With I guess what I'm looking at, PhD students at Liverpool NOC, based with Southampton University, and everything that you spoke about, I guess. There's just so much I could ask. I think it's just more of a thank you, and I probably will be reaching out to you. I've read many of your papers for my study, because I'm looking at the sustainability of relying on beach management to promote coastal resilience in sediment-starved beaches. So I think ideally, if you noticed any like patches or sediment-starved, areas while you've been carrying out this, you spoke about the accretion and erosion. Yeah. That might be a later question.
Well, I mean, the Slapton Sands, I think there's probably about 10 million cubic meters of shingle within the whole of Start Bay. So there's not a lack of sediment, even though obviously the dredging removed something like 400,000 cubic meters, so a significant amount. But there's no lack of sediment on Slapton Sands. In fact, just looking at this particular picture, the beach at the northern end, Blackpool Sands, is so wide now because of the last 20 years of this train of shingle going up to the north. I've been told that people who go to this very posh sauna at Blackpool Sands are complaining that it's too far to walk to the beach now, because they go into the sauna, and they leave the sauna, they have to walk across the beach to dip into the ocean, and it's now like almost like a 100-meter walk. Whereas at the Tor Cross end, actually in front of the seawall, there's no beach at all anymore. So there's no lack of sediment. It's just, for some people, it's in the wrong spot. I think other places on the south coast, on the Cornish coast that I've been studying, there's a lot more issue with lack of sediment than in this particular location. It's not the lack of sediment; it's where it is.
Okay, cool. No, that's brilliant. Thank you so much. I'll probably send you an email to pick it up further. Cheers.
Yep.
Great, and I think that sort of touched on a couple of other sediment related questions in the chat as well. But so I think I'll just lastly now go to Rory.
Thanks, Nish, and yeah, thanks for that excellent presentation. Hello. Given the difference in SMP policies between Tor Cross and the Lee, and the potential for terminal erosion, what's your take on the likelihood and the severity of a breach given that kind of SMP policy? And also, is there anything working with natural processes that can be done to soften that impact, if there is one?
Yeah, I mean, we've talked to the Environment Agency about this as well. I mean, of course, it's the really important question: when is it going to breach? And then, but I think it's impossible to answer that question, because, as we already talked about, the clustering, and we're bound to get another major bad winter in the next 10 years. I think had this particular winter been slightly different, had it started with an easterly, that would have acted on quite a wide beach, and would have actually added gravel to Tor Cross, and then it would have been followed by a couple of southerlies. Those southerlies would have arrived on the beach that was fuller than it was now. I think it would have been a completely different winter. So to be able to predict exactly when the breach will happen, I think is virtually impossible because of this sort of almost like random occurrence of things happening. But having said that, we do know that the shingle barrier in itself retreats something like between 30 to half a meter per year. That's a steady sort of trend that we can sort of extrapolate. We also know that the downdrift of the seawall is going to be more pronounced because of the down and end effects. So we can make some sort of projection there, and we know how wide the barrier is. But if the shingle barrier just rolls over, it can actually roll over 10, 20 meters without breaching. Breaching requires quite a specific set of conditions, because most gravel barriers, I mean, Medbury is a really good example. Medbury was quite high, was artificially maintained quite high. Then it was decided to let it manage realign, and then now it's basically retreating, occasionally overtopping, but it's not breaching. It sort of keeps its integrity, and they're just moving back as one unit. Now this can very well happen at Slapton as well. The only concern, I think, is the downstream effects. So I think from an engineering point of view, something will probably need to be done at the end of the seawall to prevent this outflanking from happening. And the outflanking will happen as a result of a series of really strong southerlies, like happened in January, probably followed by an easterly that will then take stuff away. That would probably be my mechanism for breaching. I don't think it will breach anywhere else. I think anywhere else it will roll back. We've seen the evidence of all these previous events. They've dumped shitloads, lots of shingle on top of the road. I mean, the barrier doesn't want to breach. The barrier wants to roll back and build up. The only place where it really aggressively cuts away is at these terminal ends. So that is a concern, where if it breaches at the Torcross end, so where the seawall ends, that is a potentially big problem, because that would expose the properties on the back of Torcross and increase flood risk, as well as potentially affecting the lay. I don't think it will breach anywhere else. I can't quite see that happen.
Thank you. So it's possible that the seawall might need to turn the corner, so to speak,
or something like that. You mentioned nature-based solutions. People talk about adding dredged sediment from Blackpool Sands and dumping in front of Torcross. Now that would make a huge difference, but we know the sediment transfer rates are such that we could lose 500,000 cubic meters of shingle in a single winter. So 500,000 cubic meters of shingle, if you actually nourish that, that'll cost anywhere between, north of 5 million, probably 10 million pounds just to get that. That could be gone in a single year or a couple of years. 100,000 cubic meters of shingle could go in a single storm. So again, these could work, but again, depending on when the next storm comes, it could last 1 year, it could last 5 years, but it's probably not going to last more than 10 years.
Thank you.
That's great. Thank you very much, Gerd, and thank you for staying with us for an extra 10 minutes as well. It's much appreciated. So yeah, many thanks to everyone else for attending as well. And yes, in response to the questions in the chat, the recording will be up on the website soon, and yes, you'll be free to share that as well. There's another BSG seminar coming up in a couple of weeks on the 11th of March. Can't remember what time, but it'll be lunchtime like normal, and that's a slightly different topic by Dr. Andrew Farrant, and he's going to speak about unconventional cast. So please join us for that seminar as well. But like I said, many thanks for attending, and enjoy the rest of your afternoons.